Hi and welcome. I'm trying to learn particle physics, today the standard model, and in the second part of the video we're gonna do Lagrange differential training. If you participate in the Lagrange differential training in the second half of the video, it is at your own risk. Now we're already a bit in, and now here. Thus, according to the theory of quantum electrodynamics, two electrons repel each other thanks to a photon. The boson that transmits the electromagnetic field that appears from nowhere and passes from one electron to another. Inside of a fermion there are 6 electrons, and they are repelling each other, and that's because there's a boson in the middle, and that boson is transmitting this electromagnetic field, which comes from nowhere and goes from one electron to another. An infinite series of such virtual particle fluctuations shift properties of classical or bare electrons by tiny amounts. Shifts confirmed with stunning accuracy by many experiments since the 1940s. Let's read it again and try to understand it. An infinite series of such virtual particle fluctuations shift properties of classical or bare electrons by tiny amounts. Such virtual particle fluctuations shift properties of classical electrons by a tiny amount. Why are these virtual particles? Because they come from nowhere and go to nowhere. We're talking still about the photons, which are bosons. And they are going through the 6 electrons inside the fermion and repelling them. And they're doing that by transmitting the electromagnetic field. And there's an infinite series, so that means they never end. They're doing that over and over again. And are these particles doing fluctuation? And these fluctuations do shifting of the properties of the classical or the bare electrons by tiny amounts. The properties of the electrons changes a little because they are through the photons which are transmitting the electromagnetic field repelled. The properties of these electrons are changing. Now what did we have here? Leptons, we said this about the electrons. As we have seen, the mathematical structure of quantum fields gives them an odd property. The 6 electrons don't have all the time the same property because the photon going in between all of them and repelling them shifts their property in an infinite series. And now the quantum field theory is trying to describe and saying when and how the properties are changing. So we have these electrons, and suddenly one of them weighs not 5 kilograms but 50 kilograms. These are just numbers. And we try to describe why. Because on Earth everything weighs always the same. And on another planet with another mass, it weighs always the same. But the greater the mass, the greater the gravitation. The heavier the things, basically. And now we want to say, why is this electron getting lighter? Why is this heavier? Why is this one getting larger? And so we're writing down theories and saying that happens because, I don't know. An infinite series of such virtual particle fluctuations shift properties of classical bare electrons by tiny amounts. Shifts confirmed with stunning accuracy by many experiments since the 1940s. So since the 1940s, people were making experiments and by stunning accuracy. So we can't say that they are changing in weight, size, whatever. And that can we do very precisely of these electrons. We can say very precisely others 4.545 kilogram or whatever. It took a little longer for quantum theory to tame the other forces. The weak nuclear force was... Okay, that was the electromagnetic force. The electromagnetic force is transmitted wherever it comes from by these photons, which just appear out of nowhere. No, the electromagnetic field appears out of nowhere. Out of nowhere the electromagnetic field appears, and that is transmitted through these photons, which are bosons, and which are repelling the electrons, and through that the properties of the electrons is changed inside of a fermion. It took a little longer for quantum theory to tame the other forces. The weak nuclear force was plagued by unruly infinities that made calculations of all but the simplest effects impossible. What was it here? It took a little longer for the quantum theory to tame the other forces, so that means to describe how they work. We understood now the electromagnetic force that is from somewhere does this electromagnetic force happens, and it is the photon which is transmitting that electromagnetic field force by repelling the electrons. Now it was a little harder with the weak nuclear force. And the problem with that is that there are not regular and many different calculations to calculate it. The weak nuclear force was plagued by unruly infinities that made calculations of all but the simplest effects impossible. Now, it has probably to do that there are a number. They have to say it shifts by 10, it shifts by 20. The problem is it is not like 10 or 20, but a billion or a trillion. And we cannot say it is 4 billion and 5 or 6 billion and 66. We don't know which number they are, by what number we have to calculate it, and there are many of them. Or they are infinite, I don't know what's the number here. And that makes it so hard to calculate it. If we don't know what two numbers to calculate, we don't know what the result is. If we have just one number, and we don't know the second one, how can we ever come to the result? The way forward, and it was not only possible with very simple effects. The way forward taken during the 1960s by Weinberg, Stephen Weinberg, the person here in Texas at Austin, in the university, who said that the whole thing was more or less just to, hey, we have no idea, but we have a little theory, that is it, and prove us wrong, when we know more. So, and he then, in the 60s, and also other people, was to mesh it up with electromagnetism into a unified electroweak force that manifests itself at very high energies, such as those in the early universe. The way forward, taken during the 60s by Weinberg and others, was to mesh it up with electromagnetism into a unified electroweak force that manifests itself at very high energies, such as those in the early universe. Okay, having an idea. Electromagnetism exists. I'm going to still say these are magnets. And we can calculate exactly how strong a magnet is. It's always the same strong magnet. It's not suddenly they can get weaker, but okay, whatever. It's not a magnet, I don't know what it is. And we combined the weak nuclear force with the electromagnetism, and if I put a lot of electricity, a lot of energy into it, that suddenly started to become manifest and wasn't unruly changing and shifting, so that we were able, maybe, they haven't written here, so that it then was like it was in the early universe. Okay, we will read the all in the next part. So if you're here for the standard model of quantum physics, you can go directly to the next part. We will do now I don't know the name, I don't know what we do, the language of instant training. And we're bringing the leg up, and we're pointing the foot down. The mushroom. And bring the other leg up, and point the foot down. If you participate in the language of instant training, that's the arms. They're taking the ankle of the back leg, a crane, having a straight back, and pointing the foot down. And we're taking the other leg, at the ankle, we're making a straight back and pointing the foot down. And we're doing the next exercise, one hand on tummy, one on lower back, and we bring one leg straight up. If a quad muscle is cramped, then bring the leg up and point the foot down. Try to bring the leg higher. Control with your hands that you don't fall back. Try to bring the leg higher. And bring it up and point the foot down. And the other leg. Bring it up in one straight line. Foot flexed. Try to bring the leg higher. Bring the leg up, the once foot down. Next exercise, the pipette. The standing leg points with the toes to the outside, the other leg has the heel on the ground, and we're lifting that heel off the ground, placing it again on the ground, and don't do too many. It took a little longer for quantum theory to tame the other forces. The weak nuclear force was plagued by unruly infinities that made calculations of all but the simplest effects impossible. The way forward, taken during the 60s by Weinberg and others, was to mesh it up with electromagnetism, by changing the leg, into a unified electroweak force. It manifests itself at very high energies, such as those in the early universe. There are 6 quarks, 6 leptons. 6 quarks in pairs of 3. 6 leptons. And these leptons can be electrons and neutrinos. And also bosons as like photons. They are all inside of a fermion. Force carriers are photon for electromagnetism. A weak nuclear through W1Z, and is a gluon, a strong nuclear mass giver Higgs boson. For the next exercise, the stem. Bring the foot up and down, and again up and down. Flex foot so it will not come out of the ground. And up and down, up, down, and with the other leg. Up, down. Now the horse. Have a leg in and bring it out. Flex foot in and out. Have a hand here that you don't kick yourself. And with the other leg in, out, in, out. And now you can continue with the horse 2 times. You're going to do the camel. It's a bit more difficult. So the leg up and out, while the other part of the body comes down. And one more. And now with the other leg. Leg in, leg and out. In. And now one more exercise. Have a good standing leg. You can do again with stand for camel or something, or just rest. This is a bit difficult. Have a good standing leg, but the swinging leg has a flex foot and comes up in a straight line. The other part of the body comes in the same moment down. Try to not fall in the abdomen, and try to be tall on the standing leg. And one more time. And we're changing the leg. Have a tall standing leg, a flexed foot as a swinging leg. The upper part of the body comes in the moment down in which the leg comes up. Try not to fall in the abdomen. And last 2. And we're doing just the closing exercise. Okay. And again in. We're going to close the legs. And out. That was the leg into potential training. Thank you very much, and until next time.